Hello everyone, welcome to another lecture of drug delivery engineering and principles. Let us do a quick recap of what we learned. We are now discussing hydrogels. So, we introduced the hydrogels in the last class, it is a big topic. Hydrogels is depicted here like a jelly. These are gels that are made up of very hydrophilic polymers and they can absorb a lot of water. So, we talked about hydrogels in general, we talked about polymers that are used in hydrogels. So, there are all types of polymers, both synthetic as well as polymeric as well as natural. If they are natural, they are essentially meaning that they are derived from something that is found in body. These can be sugars from the body like dextran, chitosan, these could be other kinds of proteins like collagen, fibronectin and some other body derived source, agarose, and or they can be synthetic. These are PEG based or PVC, polynipam based polymers that are very widely used. Then we talked about physical hydrogels. What are physical hydrogels? Physical hydrogels is nothing but these are gels which are formed by molecular entanglements of long chains. They may have some sort of van der Waals interactions between them or some ionic interactions, some other interaction may also be present. They may have affinity if they are biomolecules and things like that. And so, they essentially form these entanglements and results in a hydrogel formation. And then as a special case we were talking about ionic hydrogels. So, these are again hydrogels that are interacting with each other using ions. So, you can have two types of chains, one can be positively charged and another chain could be negatively charged, and they will interact with several other chains there also. So, essentially this kind of a big giant mesh is formed that results in a polymer gel being formed, which is again if these are hydrophilic polymers, then they will also have a very high absorption of water resulting in hydrogel formation. So, a little bit more on the anionic gel. So, here we are talking about, let us say we have a polyanion containing lots and lots of negative charges on that. If you put a multivalent cation, you do not even have to put, let us say another chain containing that. Let us say if you put a multivalent cation, could be calcium, could be magnesium. What will happen that these individual atoms of calcium and magnesium will interact with multiple or at least two of those negative ions, and they will result in a formation of something called an ionotropic hydrogel. And so, again there will be another calcium molecule here that will have interaction with another big chain, and so that is how you can imagine the whole network growing and making a very complex structure having lots of interaction between single chain with several other molecules. And the other cases could be you can come up with a polycation that is also contains, instead of just 2 or 3, that may also contain positive charges throughout the structure like the polyanion, and then you can have something which is a polycomplex coservate or a polyion complex hydrogel. So, depending on what ratios you are mixing them, they can either just precipitate out or they can form a gel while interacting with several other chains. So, that will essentially result in a big large network being formed just like the first case. So, let us talk about chemical hydrogels. So, unlike the physical hydrogels, these are covalently linked hydrogel networks. So, essentially whatever bonds are there, they are actually covalently linked with each other, and these covalent bonds could be again several types. We have discussed few in the polymer drug conjugates. So, these could be an EDC coupled reaction, this could be a maleimide reaction, some click chemistry. So, all of those are very feasible here, any kind of chemical bond that is being formed. So, these could be generated by directly cross linking of the water soluble polymers. So, you can have polymers that have several functional groups on them and they are water soluble, and you can directly cross link them, or you can have conversion of some hydrophobic polymers to hydrophilic polymers and then cross linking. So, let us say example I gave you in the last class was PEG-PLA-PEG, where PLA was a hydrophobic polymer. So, what I have done is I have taken a hydrophilic polymer, I have conjugated it to PEG, and now the overall this particular chain is fairly hydrophilic, and then I can have the cross linking happen between different chains to form a hydrogel cross-linked, physically cross-linked gel. So, like physical hydrogels, chemical hydrogels are not homogeneous. They are somewhat more homogeneous than the physical hydrogels, but even then you can imagine, let us say if I had these long polymer chains and I have these cross linkers that are being used to cross link them, and depending on the local concentration of the cross linker, you may have certain micro domains which are heavily cross linked, whereas the other portions may not be as cross linked. So, there might still be inhomogeneity that is present into the system. And so, if I have, let us say, a heavily cross linked area, then it will have a low water swelling and high cross link density, where, and so these can be called as clusters. So, this will be dispersed throughout the regions which may have a high swelling because of the low cross linking density. And this could be because of, again, as I said, several regions. You can have either hydrophobic interactions are also present. So, if you have now PLA, this may want to interact with another PLA of a different chain, whereas the PEG may try to separate it out, and so there might be competing force that may cause the aggregation of PLA's domain and causing a very high density of the polymer at a certain region. And so, these things can occur because of that, or they might be just because when the gel was forming there was some diffusion limitations of the cross linker, and that caused a certain region to be highly cross linked than the other. So, all of these are very feasible, but again, and they are not very homogeneous, but they are more homogeneous than, let us say, a physical hydrogel. So, hydrogel synthesis process, again this is a typical example. Not all hydrogels are going to be formed via this method, but you can have a physical gel, you can warm a polymer solution to form a gel. So, so let us say you warm it up and then slowly cool it down, and what will happen is now these chains have lots of time to interact with each other because you have increased the temperature, they are diffusing very fast, and they might find their pairs they want to interact with, and then when you slowly cool the temperature down, what will happen is they may start to form these physical gels, essentially interact with each other, van der Waals forces, hydrogen bonding, ionic interactions, all that may start happening. So, cool the polymer to form a gel. So, something like agarose is very widely used. If you guys have ever worked in a lab, you may have run DNA gels, and the very easy way to do that is to just mix some agarose in water, heat it up to make it solubilized, and then as you cool it down, these forms these gel like structure that you would then run your DNA to sort of resolve to see what sizes of DNA you have got. So, that is just one example. You can lower the pH, so that is another way you can form these. So, again, as I said, maybe some gels are more stable at a lower pH. So, you lower the pH, that may increase the interaction, that may change the charge. So, that may result in the formation of these gels. You can mix a polycation and anion at a certain ratio to get a gel. So, that is another possibility that you can use that. So, another one that is very widely used is the alginate gels. So, what is done is sodium alginate, which does not form cross link because it is only a monovalent cation. But then if you drop it into a solution containing calcium, then what will happen? Let us say if I have a beaker that contains calcium 2 plus, and if I make a drop of the sodium alginate and let it drop, what will happen? The sodium will leave the system and calcium will go in because it has higher affinity, it has 2 plus positive charge, and so what will happen is this drop will immediately polymerize to form a hydrogel of alginate. So, that is another way you can form these physical gels. And then in regards to chemical gels, it is fairly straightforward. You can have some sort of a cross linker that is present that kind of diffuses through the chains and then cross link different sections of the chain. You may have some sort of a radiation that is happening. So, maybe it is a UV based polymerization. In presence of UV, it generates radicals which then forms these polymers and then causes these polymers to form hydrogel. So, all of these can happen. You can mix different kinds of copolymers together, and they may just have functional groups that are reactive against each other and they may form bonds. So, all of that is fairly well feasible. So, here are some examples further. So, you can have a bifunctional monomers in polymers. So, it could be either a monomer or it could be a polymer, and then you mix it with some multifunctional cross linkers, and what will happen is these will go and bind to different areas, and essentially you will have cross linking happening at all these places to form a mesh like structure, essentially giving rise to a hydrogel network. Or you can have just a big chain containing several and several of these reactive places, and then all you do is just mix your multifunctional cross linkers, and they will then cross link with another chain like it's shown here, and then this may be linked to another chain. So, that is how the structure can propagate and essentially form a hydrogel network. So, when we talk about hydrogels from hydrophobic polymers, again as I said, by definition the hydrogels are made from very hydrophilic polymers. So, you have to somehow make them hydrophilic. So, you can take a hydrophobic polymer, you can modify its backbone to add lots and lots of polar groups. So, what will that result in? That will result in some sort of an amphiphilic polymer, because you have all these domains which are fairly hydrophobic, whereas these domains which are hydrophilic. And so, these domains can then interact with each other, the hydrophobic domains at several places, to sort of form a physical hydrogel, or you can then use these polar groups or some sort of other functional group to kind of cross link them at several places using an actual chemical bond, and that will result in a chemical hydrogel. So, as you can see from here also, this looks a lot more homogeneous than this does, and but again this will also have some micro domains. It will not be as well organized as is written here, because you may have some domains where you have very close, and then you can have some domains where the cross linking may not be as close as the domain showed here. So, more on the hydrogel synthesis process. So, again you can take monomer and cross linkers and co-polymerize them. You can have macromers, and then you can use a cross linker just in the way I described in the previous case, or you can have some other sort of a format. What you can also do is you can form a hydrogel. Let us say I have formed a hydrogel, and now what I do is I then add some other different copolymer or some other different monomers into that, which then diffuses throughout this network, which is small enough to go into these pores of these, and then I add another cross linker. So, let us say there are now, let me let us say if I am basically having another different chain that comes with another cross linker and cross links it. So, basically now what I am looking at, I am looking at a domain where you have two hydrogels that are just sort of interlinked with each other. So, the chains are crisscrossing through all these polymer networks, and that is essentially causing them to crisscross with each other, causing this kind of interpenetrating hydrogel network. So, you cannot separate out the two gels, because the chains are actually physically entangled with each other, but then the two hydrogels are actually separate. If you can have separately formed them together, but now what you have done is you form them in situ in together in a single system. So, these are called interpenetrating hydrogel network. What are the advantages of such a system? These can have very favorable properties. You can have let us say one gel which is structurally or mechanically much stronger than the other, but then the other gel may be good for the cells. So, what will happen now, because now you have formed them together into a system, it will also be mechanically good, as well as the cells can still attach to it using the other hydrogel network. So, these are some of the advantages here. So, what are some of the structure and properties of the hydrogel? So, let us define some few terms. So, these are some of the most important terms in terms of defining hydrogel. So, one is polymer volume fraction in the swollen state. So, this is defined as V2S. This is essentially just a measure of how much amount of fluid that the hydrogel can incorporate into its structure. So, you can have a polymer, you know what is the volume of that polymer that you started with, you then form this hydrogel and then you see what is the final volume of this hydrogel. So, now you can have some sort of estimate as to what is the V2S is as well as how much water it has absorbed. So, V2S is nothing but the volume of the polymer divided by the volume of the solvent gel. So, that will give you essentially Vp by V gel defined as 1 by Q, which is sort of an estimate of how much the swelling has actually happened. So, if this comes out to be let us say 90%, then only 10% is water there, whereas this comes out only as 10%, then it is almost has swelled 10 times compared to its original volume. Then you can have effective molecular weight of the polymer between cross links. So, let us say if this is the cross link, and again as I said there will be non homogeneous, so some cross links might be fairly well apart and some might be very close together. So, this is sort of an average effective cross linking of this and it is defined as MC, and so MC is nothing but the distance between the two cross links on an average. And then you can have a network mesh or a pore size. So, very similar to the MC, which is the effective cross linking, is essentially what is the pore size. So, what diameter pore are we talking about, what sort of a, how can we define the distance between the different polymer chains, and so this is sort of a measure of what is the network porosity. So, some network pore size calculation, one of the most important parameters in controlling the drug release rate is what is the pore size of this. The mathematical expression of the pore size is given by nothing but the pore size is equal to alpha r naught square square root, and what that is alpha is the elongation of the polymer chain. So, let us say if my polymer chain is of a length L, after the formation and elongation it becomes L plus delta L. So, now we are talking about alpha is basically the elongation of this chain, where r naught is the unperturbed end to end distance between the polymer chain between cross links. So, let us say if I make these cross links, this distance is r naught, and to make sure that the signs are not changing and all, so this is r naught square under root, and essentially this can then elongate as the swelling is happening and further increase, and that is how you can then define the pore size here. So, one way you can do is you can do some microscopy, it could be electron microscopy, it could be some other form of microscopy to sort of determine what is the distance between these two units. Then the next thing comes about the diffusion in the hydrogel. So, let us say the pores are big enough or the pores are not big enough, how does the drug diffuse from such a system? So, release of drug and solids from the hydrogel matrices is defined by the diffusion into the polymer in that polymer network. So, there are mass transfer limitations due to the network structure itself. So, it is necessary to understand what is the fundamental mechanism of this transport. So, if it is a diffusion control release, we can use the Fick's law, right. We can just write the Fick's law where the flux is equal to the diffusion coefficient, whereas the change in the concentration. So, that is to start with. So, let us say the diffusion in hydrogel there is a constant d that we are going to consider. So, for time dependent release we will basically invoke the second law, so which is then defined by this in one dimension. So, if the diffusion coefficients are constant and we are assuming that outside whatever the drug is going to come out outside is going to immediately get sucked away, then we can then define the boundary conditions here as is defined here. At t equal to 0 we are saying that x is essentially less than delta by 2, which is essentially the concentration of the drug is defined here, and at this point 0 at t greater than 0 we are saying that delta c is del c with the distance x is 0. So, we put this all, we get a Fick's law solution which is this, and if we only consider early time points we can neglect few of the terms and then we get the release will be like this. Okay, I hope this is understood. Again, we do not need to go into the derivations of these differential equations, but using the Fick's law and putting in the boundary conditions we are getting a solution which looks like this, and at early time points we can then simplify it using this. and early time point is when this is most important. As I said, the hydrogels do not really release the drug for too long. So, we will just talk only about the early time point here. So, now how does the network morphology, I mean, so again in the previous case we have not really taken into account anything that has to do with the hydrogel. So, how does the role that now it is in the hydrogel plays. So, now that the drug is released from the hydrogel, the drug diameter as well as the size of the network becomes important. So, we can now classify the hydrogels into different forms. It could be macroporous or microporous. So, as the name suggests, what is macroporous? Macroporous essentially mean it is large pores, macropores. Typically we for biologically relevant things we are talking about 100 nanometer to about a micron. So, the solute transport is hindered by the presence of the molecular mesh. Of course, the drug is going to collide with the mesh as well, and so the different factors that we can then introduce is one is the diffusion coefficient in the pure solvent. So, let us say if there was no mesh, then the diffusion coefficient would have been DIW. Now, another thing we are defining is network porosity that we already defined, and tortuosity, and then now the drug may have some partition coefficient, right, because it may have a different solubility between the outside water as well as inside the gel. So, let us say that partition coefficient is defined as Kp, then we can use these terms to modify the equation that we just listed in the last slide. And the way we will modify that is we will say that the D effective is, now we are saying the D is not constant, right. So, we are saying the D effective is then gets multiplied by first of all the partition coefficient with the D in the solvent, then what is the network porosity. So, higher this is, the higher this term is, higher the tortuosity, the lower the D effective will be. So, this essentially becomes a D effective. So, that is the new D effective. And now this D effective is going to change locally if there are micro domains, but we will neglect that for now. What about a microporous hydrogel? So, as the name suggests, micropores are essentially we are talking about smaller pores, they are not as big as what we defined earlier. So, these are could be 100 Armstrong to 1000 Armstrong or even smaller. So, these pores are water filled and the transport across this is essentially by molecular diffusion and convection in the water filled pores. There is a lot of partitioning that is going to happen on the solute within these pore walls, and this can be described in a form similar to the macroporous gels with a reduction factor. So, now we are saying that this essentially this partition coefficient is going to change, and there is another reduction factor Kr that we are adding, which is a fractional reduction of the diffusivity when the solute diameter is comparable, right, because now there will be a lot more collisions that is going to happen between the chains and the network and the drug that is being used to deliver. So, an example, so here we are talking about a PLA-PEG-PLA hydrogel. So, as the name suggests, so we have a PLA domain. Remember PLA is lactic acid polymer, so they have these ester groups. We have a PEG domain, and then we have again this ester domain with PLA, and this is, as you can see, is a ether domain. Right. So, let us say we are talking about that. In this case, in this example, we are saying that the terminal acid group has now been modified with acrylate group. So, what does acrylate do from our past discussions? It can get activated from free radicals in the presence of UV light. So, when the light is shown on it, what will happen is these acrylate bonds will get radically polymerized by reacting with the other acrylate groups. So, let us talk about some of the release from this. This is actual data from some papers. So, what they did is you can see they got a certain release over a certain time. So, this is the release of the protein that was encapsulated, this is on the basis of time. So, as you are decreasing the polymer concentration from 50% to 20% to 10%, what you are saying is the release is increasing, right. So, let us say this is 50%, this is 20%, and this is 10%. So, what does that mean? That means when I say 50%, that means that the polymer is about 50% in the whole volume, right. So, almost let us say if I make a 10 ml gel, then I am saying 5 ml of that is the polymer itself, or 2 ml of that is a polymer for 20%, and then similarly 1 ml of that is a polymer. So, what we are saying is the chains are becoming more and more as you are increasing the polymer concentration. So, what will happen if there are more chains in a confined area, that will, what will happen is, let us say I have these chains, and if I increase the polymer density within this area, now instead of having 2 chains I will have 4 chains, 5 chains. So, what has happened is the pore size has decreased quite a bit. So, that has been reflected as the release rate, because now that the pores has decreased quite a bit, it is causing it to in this direction it is slowing down, whereas if you go in this direction where you are decreasing the polymer concentration, then more and more BSA is coming out very rapidly. So, as you can say for this 50% gel in this particular case for BSA, it took about almost 50-60 days for all of the amount to come out, whereas as you are decreasing it, this is now changed to 20 days or 10 days for 10%. What is going to be the effect of increasing PLA fraction? So, what will happen now if I increase the PLA? So, what is PLA in this case? PLA is sort of a when I am saying the fraction, I am saying that essentially the PEG component is the same, but the PLA that is attached to it has increased. So, this is going to increase the molecular length of this. So, what will happen as I increase the PLA units, now I am talking about longer chains, right, and so because these are longer chains, what will happen is now the release rate is actually going to increase as I am increasing the PLA. So, this is going to basically cause the proteins to come out even faster. Here is another example. So, in this case they have used BMP, which is a bone morphogenic protein, very widely used for bone regeneration applications, and osteoblasts are nothing but cells of the bones that are involved in bone formation activity. ALP is a measure of how much bone they are forming. So, it is an enzyme that if the more bone is being formed, the more enzyme will be there. And so, you can see there are 3 cases here. One is essentially, so each of these bars are, so the black bars are 1 week data, the white bars are 2 week data, and the hash bars are essentially striped bars are 3 weeks data. And so, what you can see, you can have a hydrogel and you have no growth factor, you can just have growth, just have the cells in 2D, and you will have a certain amount of ALP activity as the time progresses. So, limited amount here, you can add just the growth factors to them, and this increases a bit of the bone formation, these growth factors, which is essentially BMP here. You can put it in a hydrogel, and now because it is in a hydrogel itself, that itself, because this is a more closer environment to what they see in 3D, the cells are itself compared to this guy, the cells are increasing the bone formation, and now if you put further the BMP in here, that is going to further increase the bone formation now, because the BMP is slowly being released and it is being used by these cells to form these bone. Okay. So, we will stop here. We will continue in the next class, and I am going to talk more about hydrogels, and in the next class we talk about in situ hydrogels. So, see you then. Thank you.